Variation of chemical properties of the representative elements. So we know ionization energy measures the attraction of an atom for its own electrons, whereas the electron affinity expresses the attraction of an atom for an additional electron from another source. The periodic table also tells us about metallic character. Metallic character decreases from left to right and increases from top to bottom. So metals, which have low ionization energy and low electron affinity, that describes metallic character. Elements in the same group may have similar properties because of similar electron configuration, but you have to apply this with caution. All right, so there's a couple twists to this. They have to be the same type of element, metal, non-metal, but also the elements in row 2 of each family actually differ from the rest of the group, and it's most likely due to the small size of the atom. So lithium, while it shares some characteristics of the rest of the alkali metals, it does have some differences than potassium and sodium, and we'll look at that when we look at each group individually. Density is another trend that's on the periodic table. So we know that density is mass per volume, and it's actually a V-shaped trend where the point of the V is at osmium, which is OS, number 76, and iridium, IR, which is number 77. So those two are the most dense, and then it gets the density decreases as you go out in a V shape. So this is taking into account both the volume, the atomic size, and the mass of the atom due to protons and neutrons. So there's a diagonal relationship on the periodic table as well, and it shows the similarities between pairs of elements in different groups and periods. So again, group 2 is different from the rest of its group members. However, it does share more common properties with the element that it's diagonal to. So lithium and magnesium actually share a lot of similarities. Beryllium and aluminum share a lot of similarities. Boron and silicon. And you can kind of do that diagonal the rest of the way as well. The reason why we see this diagonal relationship is because of the closeness of the charge densities of their cations. Charge density is the charge of the ion divided by its volume. So hydrogen, which is 1s1, hydrogen is special because there's really no place for the hydrogen to fit on the periodic table. Some periodic tables show it in group 1, but it's not really a metal, so it shouldn't be there. Sometimes it's shown near helium, like in group 17, but it's not a halogen, so it really doesn't belong there. So sometimes it's actually shown up above the periodic table, separate, all by itself, kind of free floating. So why is hydrogen so difficult to place on the periodic table? Well, it has a single s valence electron, like the alkali metals, which is why it's normally found there. It forms a unipositive ion, or H+, and that can be hydrated in a solution to form H3O+. It can form a hydride ion, or H- in an ionic compound. So that's like the halogens forming their negative ones. Ionic hydrides react with water to produce hydrogen gas and metal hydroxides. And the most important form of hydrogen is water. And water is formed by burning hydrogen in air. Now, group 1A elements all end in NS1 as long as the energy level is above 2 or above, and those are your alkali metals. They have low ionization energies. They have the tendency to lose their valence electron, so they form a +1 charge. They're very reactive, so they're not found in nature in their pure state. Instead, they're always found in stable compounds. They react with water to produce hydrogen gas and a metal hydroxide. When exposed in air, they lose their shiny appearance because they're forming oxides, like lithium oxide, Li2O. Lithium would form the oxide. The rest of them actually form peroxides, so Na2O2, sodium peroxide. Potassium, rubidium, and cesium can actually form superoxides. Now, a superoxide is O2 minus 1. So as you go down the oxide is going to change a little bit. One of them is going to be oxygen, the other one's going to be peroxide, and then your superperoxide. So that's different as you go down. So these are some pictures of our group 1 elements. Notice that they all look very shiny, metal-like. None of them really have any color. And if we were to cut into it, it would start to appear very dull because it would be reacting with the air. Group 2 elements are your alkaline earth metals. They're somewhat less reactive than alkali metals, but more reactive than your transition metals. They have a tendency to form a +2 ion, so they're losing their 2 valence electrons. Most beryllium compounds and some magnesium compounds are actually molecular rather than ionic in nature, and that's due to electronegativity values. Beryllium doesn't react with water. Magnesium will react slowly with steam. Calcium, strontium, and barium actually react with cold water. So again, we have this trend of reacting with water in our group 2. Reactivity with oxygen also increases down the group. Calcium, strontium, and barium will actually react with acids, but magnesium and beryllium do not. Calcium, strontium, and barium will produce the hydrogen gas when they react with an acid. But since they also react with water, there's actually 2 reactions going on simultaneously. And then one interesting thing about strontium is that it's a major product of the atomic bomb. So if the atomic bomb explodes and strontium gets in the atmosphere, it can settle onto the earth and get into our food chain. If we start eating the food then that has that strontium-90 isotope, it will actually replace the calcium in our bones. So instead of Ca+2, we'd have Sr+2. And that can cause us to have anemia, leukemia, and other chronic illnesses. Group 3A elements, or group 13, is interesting because we start to see different types of elements in the groups. So boron's a metalloid, everybody else is a metal. Boron doesn't form binary ionic compounds and is relatively unreactive towards oxygen and water. Aluminum, the next element down, is reactive with oxygen, and when it's exposed to air usually has a protective coating of aluminum oxide, which is less reactive than pure aluminum. And aluminum only forms tripositive ions, Al+3. So in our picture of aluminum down here, all of that is actually coated with oxygen or aluminum oxide. It's not pure aluminum. Other metals underneath aluminum in our group 3 can actually form +1 or +3. The +1 ion becomes more stable as you go down the group than the +3. So gallium would be +3, but indium might want +1 more because it's more stable form. Metals of group 3A may also form molecular compounds. So we're starting to see the shift from ionic to molecular as you're moving across the period into the different groups. So group 4A elements, we have carbon, which is a non-metal, and it can be in graphite or diamond form. You have silicon and germanium, which are metalloids. You have tin and lead, which are metals and don't react with water, but they do react with acids to form hydrogen gas. These elements form +2 and +4 oxidation states. Notice I said oxidation states and not charges this time. Carbon and silicon will form that +4 oxidation state, which is more stable for them. But as we go down the group, we start to notice that +2 is more stable. So tin typically is a +2, and lead is almost always a +2 because it's a much more stable form of lead. Group 15, now we have nitrogen and phosphorus, which are nonmetals, arsenic and antimony, which are metalloids, and bismuth, which is a metal. Nitrogen is a diatomic. It can form many number of oxides, so you can have NO2, NO3, N2O4, and we refer to those as NOx, N-O-X, where we can have X being any type of subscript. The tendency for nitrogen is to accept 3 electrons to form N-3. Now phosphorus actually exists as P4 molecules, and notice that in the picture we have both a white and a red form of phosphorus. And that would go along with the 2 different solids that it could form. So some important oxy acids would be our nitric acid and our phosphoric acid. They're formed when nitrogen and our nitrogen oxides and our potassium oxides react with water. Arsenic, that should be Sb. Antimony and bismuth have extensive 3D structures. Bismuth is far less reactive metal than those in the preceding groups. So again, as you're moving from left to right across that period, we're decreasing the reactivity of the metal, so bismuth is less reactive. Group 6A, you have oxygen, sulfur, and selenium, which are nonmetals. Tellurium and polonium are metalloids. Oxygen exists as a diatomic. Sulfur and selenium actually form molecular formulas of S8 and Se8. Tellurium and polonium exist as extensive 3D structures. Oxygen, sulfur, selenium, and tellurium tend to gain 2 electrons to form -2 charges. In our pictures, notice that sulfur is yellow. That's a very distinct color for sulfur. Group 17, or our halogens, are all nonmetals and they're all diatomics. Now we're not talking about astatine because it's actually radioactive and we don't know a whole bunch about its properties, and some periodic tables actually label it as a metalloid. So the rest of them, from fluorine down to iodine, are very reactive and not found in elemental form in nature. Fluorine is actually so reactive it will attack water and generate oxygen. It will also eat through glass or etch or mark glass. It will react with the elements in the glass. They tend to have high ionization energies and high electron affinities, so they're very reactive. We call the anions of halogens halides, and they're all isoelectronic with the noble gas that's sitting to the right. Something interesting to note is that HF is actually a weak acid, while HCl, HBr, and HI are all strong acids. Now look at the picture, some of the colors that you need to be aware of. Chlorine is actually a yellow gas. Bromine is considered a orange-brown gas. And then you have iodine, which is a lovely purple gas. Group 18, or our noble gases, all exist as monatomic species, so it's one single atom by itself. They have completely filled S and P subshells, giving them great stability. They have the highest ionization energies and have no tendency to accept electrons, so their electron affinity values are typically 0. They were thought to be inert, and in Chem 1 we do say that they are inert, but actually xenon and krypton can form molecules. So a British scientist, Niall Bartlett, created noble gas molecules with xenon and krypton, but there's actually no major applications in industry for them. So while they can exist, they don't really do anything. Alright, so if we compare group 1A and group 1B, which is actually group 11, your copper group, they both have an outer configuration of NS1. Remember, group 11 will steal 1 from the S to fill the D. So their properties we would think would be the same, but they're actually very different. The first ionization energy of group 11 is higher than group 1 because they have incomplete shielding of the nucleus by the inner D electrons. So that makes the group 11 much less reactive. The outer S electrons then are strongly attracted to the nucleus. Copper, silver, and gold are actually unreactive, so that they're usually found in nature by themselves. The inertness, or the non-reactivity of them, and the rarity of them makes them valuable for manufacturing coins and jewelry. So that's really why we use copper, gold, and silver, and why they're worth money to us. So that one particular group can actually be referred to as the coinage metals. Finally, elements tend to react similarly, or there's even trends with how things react to specific items, like oxygen. So if we look specifically at row 3 and how they react with oxygen, you can kind of see this trend. So oxygen we know has a tendency to form the oxide ion O-2, and is greatly favored when combining with metals that have low ionization energies like group 1, group 2, and aluminum. As your ionization energies increase across, so does the molecular nature of the oxides form. So if you look at the data table, this is kind of summarizing it all for us. Sodium oxide, magnesium oxide, and aluminum oxide are all ionic compounds. And then you get to silicon, phosphorus, sulfur, and chlorine, and those are going to be all molecular oxides. Silicon dioxide actually exists in huge 3D networks where our ionic compounds exist as ions, and then the rest of the molecular, phosphorus, sulfur, and chlorine, exist as molecules, discrete units. Another thing to bring up here is acidic oxides produce acids in water. So our molecular oxides, silicon, phosphorus, sulfur, and chlorine, will actually form acids when they're put in water. So you get your H3PO4, your H2SO3 or SO4, your H2ClO3 or HClO3 or HClO4 or HClO2 or HClO. So those are all acidic oxides. Your basic oxides produce bases in water, and that would be your ionic oxides, or your sodium, magnesium, and aluminum. Your sodium and your magnesium. When you put those into water, you actually get sodium hydroxide and magnesium hydroxide. Now, amphoteric means that it could go to basic or it could go acidic, and your aluminum oxide actually does that. And we'll get more into depth with those types of things in our acid-base unit.